Okay, so I was told that there is some blind spot on this blackboard. So maybe I should draw a line where people can see. Can people see this?
Above there, it'll be okay.
Above. All right, so let's draw the line. Yeah, it's- Right, how about that? What about down here? Is this in the back? Can people see the, no? So where's the cutoff? Somewhere here? Yeah? All right. All right, so last time, I think just before lunch, I was trying to convince you this is one of the few actual formal classifications we'll do. Everything else will be trying to connect things to other things we know, or doing this Dirac kind of a classification, looking when we have a mass term and just one mass term, and approaching it that way. But the one thing I would like to kind of try to classify is this the topology of these chirally symmetric states, chirally symmetric insulators. They have a matrix that anticommutes to the Hamiltonian, and you can always write the matrix like that. This is the matrix that anticommutes, and it's purely off diagonal in that basis. And to make it Hermitian, you need that these are Hermitian conjugates of one another, but otherwise arbitrary. Okay, but we also said that we're going to be interested in gapped Hamiltonians. So there's a gap separating the negative and positive energy states over here. And for convenience, we'll make all of those energies equal to 1. Okay, plus 1 and minus 1, which is called flattening the Hamiltonian. And it's analogous to, in the beginning, when we were talking about Bery's phase, we took a unit vector rather than the most general vector to describe the 2 by 2 matrices. And so we can flatten it. Essentially, it amounts to just focusing on the wave functions, right? You find wave functions that are being occupied, and you kind of ignore the particulars of the energy dispersion. You just flatten it. And after that flattening procedure, the square of the Hamiltonian is just the identity. Okay, the energy eigenvalues are plus or minus 1. Square it is all plus 1. It's identity. You can implement that by taking Q to be a unitary matrix. Okay, so the most general flattened Hamiltonian with chiral symmetry has a unitary matrix up over here. Okay, so the problem now reduces to classifying the following maps. We have a one-dimensional Brillouin zone. It's periodic, so it's essentially a circle, S1. I want to think about this Q, which defines my flattened Hamiltonian, this unitary matrix Q, at every point on this Brillouin zone, and that defines a map to the space of unitary matrices. Okay, these are UN unitary matrices that depend on the dimension of this thing, and we're going to think of n being large in general, although for specific computations we may take smaller values and check that things work. Okay, so it's actually known that this, if you look at topologically distinct maps, so what do you mean by topologically distinct? So let me say I have two Hamiltonians, which I want to check if they are topologically distinct. Let's call them H1 and H2. Then the question is, can you find a sequence? So H at lambda equal to 0 is H1, and H at lambda equal to 0 is lambda equal to 1 is H2. Okay, so can you continuously interpolate between 0 and 1 for lambda? Find a sequence of these Hamiltonians where the gap remains open throughout. Okay, so that identifies both of them as having the same topology, and in that way you can create an equivalence class of Hamiltonians. You pick a Hamiltonian, find all the other Hamiltonians that can be related to it via this sort of smooth deformation. Okay, it's your sort of intuitive notion of topology, and we want to know how many such classes there are. Okay, those are the topological distinctions. That's really classifying the topologically distinct maps from the circle to the space of UN unitary matrices. Okay, and just to do this computation explicitly, let's consider the case when n is 1. Okay, so U1 is just a phase. Okay, that's a unitary matrix, 1 by 1 unitary matrix. And that's essentially what we have over here for this particular model. This off-diagonal component is just some complex number. If you were to flatten it, if you were to divide by the norm of this number, you would get a pure phase. Okay, so we can check what does this particular Hamiltonian correspond to when I think about it in terms of these maps. Okay, so let's do that. Let's look at this particular complex number and see what it does as I vary the k inside the Brillouin zone. Okay. Yes, of course, this depends on whether you're in the which of the two phases you're in. Okay, so let's say you're in the phase where T1 is greater than T2. Okay, so then you have a complex number. The norm of this one. Okay, and if you plot this, so let me actually plot just the numerator. It's easy enough to see from that. So T1 is some number, and then you rotate around that. It looks like that. Okay, and of course, if you flatten this onto a circle, it will. I guess it will look something like. You have the circle, which is the phase of this number, and what it does is it makes an excursion. It does that and comes back, right? So it does something, but this is a topologically trivial map in the sense that I can shrink this to a point. Okay? On the other hand, if I look at the T1 less than T2, you do the same thing now over here. Again, let me just plot the numerator first. You have this T1 here, and then this some circle. So that's a circle, believe it or not. And so if you flatten this, this would go all the way around. This would go all the way around the circle. So you see that these two cases actually represent topologically distinct maps, and the mapping of the Brillouin zone to the circle, of course, is the equivalence classes, the really topologically distinct maps, are labeled by an integer, okay, which is the number of times you wrap around the circle. Okay, so of course this is for the case of for n equal to 1, but it turns out to be true more generally. If you have a general unitary matrix, it remains true. And you can actually write down an invariant that you can calculate. Give me a unitary matrix, and there's an explicit expression for this winding number. This Q is, of course, a function of K. It's a unitary matrix. And of course, if this was a pure phase, this is just the gradient of the phase. You integrate the gradient of the phase, and it appears to be 0 because it's the integral of a total derivative. But of course, the phase is not a single-valued function, and you can end up picking up multiples of integers, okay, or multiples of 2 pi, I guess, and it's properly normalized. But then you can generalize this to any n by n unitary matrix. And you can show that this is, again, a quantized invariant. Yeah?
For the special case when n equal to 1, it looks like when we do some sort of a gauge transformation, that kind of change this qk. Like if we rewrite the matrix H of k as a function of a new basis ak and bk e to the power I phi k or something like that. That kind of looks like it's going to affect this topology.
That's a good question. So, um, yeah, so one thing you could say is that if you look at the relative, so there's something a little strange about this SSH chain, which I'll talk a little bit about, which has to do with the edge states. So if you look at the edge states, so we said there are two limits, right? Like that. And so these are the two phases that we are distinguishing, where these are the strong and the weak bonds. You only get edge states when you cut it along one of them, right? And a more proper phase is when you combine these two. Okay, when you combine these two, regardless of where you cut it, you will have an edge state. So the thing that is well defined in the SSH chain is the relative topology between these two. So if I give you two phase factors Q and apply the same gauge transformation, of course the relative Q is the relative quantized invariant is still preserved. Yeah, it may have to do with that. But that's a good question. We'll talk more about that. Okay, so so anyway, this is one of the notes that if you want to get edge states or a robust topological phase, you really want to combine two of these chains, and then the two phases look like that. Okay, and if you think of these, for example, as sites, okay, then this one will have edge states over here when you cut it, and these will not. Okay, so yeah, so I won't go through the argument for deriving these edge states, but I'll, there are several standard references for this. So there are two limits where you can derive the edge states for the for this SSH chain, which reduces to this invariant. One of them, of course, is to just solve the Dirac equation, which we had over here, and where you change the sign of this mass. So you solve okay, so using the Dirac theory. It's sort of a standard computation. It's in my notes. The other thing to do, of course, is to solve it within these cartoon pictures. So really go to the limits where you switch off one or the other hopping, put them together, things like this, and verify that you have some site in between where you have a zero mode, a gapless excitation, while the bulk of the system has a gap. Okay. Yeah, so that is a direct consequence of this topological quantity. Maybe. Okay, and one of the exercises, which may be nice to work out, is a little bit subtle actually. Okay, verify that these are compatible. Okay, so these two ways of looking at the edge mode are compatible. For example, one thing you may want to check is on which sublattice the zero mode lives on. Yeah, so these are really two opposite limits. This is like a limit near the transition. This is really comparing two phases that are deep on either side of the phase diagram. They should give you qualitatively the same physics, but you can actually look into the details and see how they compare. Okay, so that I'll leave as an exercise. Okay, so this tells you that there is this topological invariant, this integer topological invariant in one dimension for this particular class. So we have one entry in this table. In one dimension we have, so this is the spatial dimension. This A3 is some strange terminology to refer to this, this Carli symmetric class. So this has some symmetry, and we are saying that there is phases that are distinguished by some integer index. Okay, so that's what that entry means, and we want to fill out the rest of this table. I'll explain what these other classes mean. But this particular class is very simple to explain. Class A, it's simply the class of insulators which have no symmetry. Okay, so we're just going to think about insulators which have no symmetry. That is going to be class A, and we'll try to fill out what to expect for them in different dimensions. Okay, so in a way, we already looked at it in dimension 1 when we did this analysis over here. Okay, so in one dimension, we said this is the effective theory that you can write down at low energies, and having a single mass term gives you these distinct phases of class A3, but now you relax the symmetry condition. You say there's no symmetry constraint, and then you're also allowed to have this additional mass term. So two mass terms, which means that you can go from one phase to another, avoiding any kind of phase transition. And you can also argue more generally that in this particular dimension, there are no topological phases. Okay, so I'll write a 0 over here, which will indicate no phases. Okay, no distinct phases. Everything can be smoothly deformed into everything else. All insulators are in one dimension essentially identical in the absence of symmetry. Okay, but what about the other dimensions? For example, what about 2 dimensions? Okay, and so let's look at that. But before we do that, let me actually finish this story about this class A3. So it turns out you can write such an invariant for any odd dimension. Okay, so you can generalize this Q. Okay, so you can, when you have an odd number of these derivatives, you can just take the product. Okay, so maybe I should write IJK. EDC is a better choice. And again, you can argue this is a topological invariant. If you make small changes in Q, you can show that this does not change. And for a particular choice with some proper normalizations, this will give you integer invariant. Okay, so of course this requires special pleading to say this happens, but we'll find a simpler way of filling out this table. But just to anticipate this, we're going to get a Z in all the odd dimensions. Okay, for this class A3. Okay, so but now we'd like to fill out the rest of this. So for example, we want to talk about this particular case, which actually is the most interesting case. So insulators with no symmetry in 2 dimensions. And that's the case where you get a Chern insulator, and we want to think of various ways to do that classification. Okay, so first let's start with a kind of a sophisticated sort of viewpoint, which is doing the analog of this, but in that particular symmetry class. Okay, so let's think of what we'd have to do if you wanted to kind of reproduce or sort of follow that line of reasoning. Okay, so the first thing we need to do is to have a way to represent Hamiltonians corresponding to that particular symmetry. Okay, so let's call this class A. Okay, and we want to think about maps if you're going to look in 2 dimensions. So let's call this some space B, which will, I'll tell you what it is. It's not super illuminating, but we'll have a way to represent the space B. And then what I want to do is I want to think about the Brillouin zone. Okay, which is essentially a 2 torus. T2, you can think in terms of pictures if you like. And you want to find all the topologically distinct maps from this 2 torus to this particular set of Hamiltonians. Okay, things that you cannot smoothly vary from one to another. Okay, so it turns out this is a little bit of slightly technical thing which we believe works, which is if you really want to find phases in 2 dimensions, it turns out you can replace the torus by the sphere in the same dimension. Okay, so instead of thinking literally about the Brillouin zone, imagine some version of the Brillouin zone which actually lives on the sphere. So you have 2 coordinates, kx and ky, but the sum of their squares are supposed to live on the sphere, and we want to think about maps from the sphere to this particular space. Okay, so this just the reason this works essentially is the difference between the torus and the sphere are these cycles, which actually represent lower dimensional topological phases. Okay, you have certain translation symmetry implicit in the torus, which is not there in the sphere, but that translation symmetry ends up giving you phases in lower dimensions. So it's sort of these weak topological phases, not things that are intrinsic to that particular dimension. Okay, so you actually want to forget about that. You want to think about states that are present in the absence of translation symmetry eventually, even with disorder, and for that it's sufficient to replace it by the sphere. So we have the slightly simpler problem of mapping the sphere to this particular space. Okay, so what is the space? We want to think of Hamiltonians. Again, I'm going to think about Hamiltonians where the energy eigenvalues are +1 or -1. Okay, and there's going to be n of these and m of them. Okay, so unlike the case with chiral symmetry, there's no reason for the positive and negative energy eigenvalues to be of the same number. Okay, there's really no symmetry over here. So these are the eigenvalues of h. Okay, so again, h squared is equal to 1. This is the flattened Hamiltonian I'm thinking about. Okay, so any such Hamiltonian you can write in terms of a reference. So the reference Hamiltonian has all the eigenvalues 1, -1, okay, the right number of them. So n of them are 1 and m are -1. Okay, so it has these eigenvalues, and then, of course, you're free to choose any unitary rotation of this. Okay, in other words, you're free to choose any vectors that correspond to these eigenvalues. Okay, that's the most general Hamiltonian at each point in K space. Okay, so it may appear at this point, all I need to do is to specify this U matrix, which is a U n plus m unitary matrix. Okay, well, that's not quite right, because there are some unitary matrices that actually do nothing. Okay, so if I imagine a unitary matrix that only acts on these positive energy states and rotates them. Okay, so those are just rotating this identity matrix around, and that's not actually changing the Hamiltonian. So those kind of transformations are really not contributing to new kinds of matrices. So it's a redundancy in your parametrization. You want to get rid of that redundancy. So this is actually a quotient. You want to divide out by unitary matrices that do nothing to this to the spectrum. Just mix the unoccupied bands or just mix the occupied bands. Just a different basis there. Okay, so this is really the space that we want to think about. At every point K, we have the space set of unitary matrices, n plus m dimensional, mod n and m dimensional. And you want to map the sphere to this space. Okay, so distinct maps of the sphere of the space, it has a standard notation. So this pi2 tells you this is maps from the two-dimensional sphere to the space. Okay, and this is known to be Z. Okay, again, we'll give some simple-minded ways of explaining this, but this thing is known to be Z. Okay, so this entry over here is going to be Z, and you see it'll turn out it's not a coincidence that it's flanked on either side by these Z classifications in the other symmetry class. And that's how we'll actually eventually argue for this, the most rigorous way of arguing for that. Okay, but before that, let's use our simple kind of simple-minded arguments to see why you may get distinct phases in two dimensions in this symmetry class. Okay, basically no symmetries. Okay, so the first thing we did, the first sort of check we did, is to look at some finite dimensional version of the space, okay, rather than the most general n and m dimensional number of bands. Let's just think of the simplest case, which is one band above and one band below. Okay. Okay, so this isn't conclusive. Sometimes you end up, when you have a small number of bands, you end up getting topological states that when you add more bands go away. Okay, but it's a first check. What if you have just these two bands, one above and one below? Okay, but this is a two-level system. Yeah.
Sorry. Suppose you're given some Hamiltonian. The way you actually make that, significant ones that minus ones is to find basically the eigenvalues and then divide them by their.
Yeah, that's right.
Is there an easy way to see why all the Hamiltonians that end up in this form are equivalent?
So if you think about, so this you can always do this for a gapped Hamiltonian. That's kind of important. So if I have some band with some band dispersion like we had for the one-dimensional problem, so what you want to do is you want to, by a sequence of transformations, you want to get it to that, something that looks like that. So you want to preserve the eigenvector information. You're going to retain exactly the same eigenvectors as you have over here, but eliminate the the eigenvalue information. The only part of the eigenvalue information you've kept is that it's above 0. It's an unoccupied band or an occupied band. And if you like, you don't have to think of it as a Hamiltonian. You can think of it as this particular projector. And this is what you need to classify. And that makes sense because details of the dispersion are not going to affect the topology. They're going to make your life harder, but no, they're not going to affect the topology. Going from here to there, there's no gap closing, for example. Yeah, so when you have this case, you have a two-level system with where the Hamiltonian squares to 1. Okay, we know exactly what that is. That's simply this can be expanded in terms of the Pauli matrices in terms of a unit vector D. Okay. That's the 1-by-1 case where this Hamiltonian squares to 1. Okay, so in this case, when I want to know the topologically distinct maps, I'm going to map the sphere, which is actually the two torus in disguise, simplified for us. I'm going to map the sphere to the sphere. Okay, the unit vector is also defined as sphere. And we know that these maps, just like circle to circle, sphere to sphere is characterized by an integer, which tells you how many times you wrap around the sphere. Okay, you could take this entire sphere, map it to a point, let's say the North Pole, or you could take the degree 1 map where each point in the sphere maps to the corresponding point in the other sphere. So it's a degree 1 map. It wraps the sphere once, and 2 and 3 and so on. Okay, and if you go back to our discussion of Berry's phase, this corresponds to a map from this from a 2-parameter space. We call it T and lambda, where you cover the entire sphere, and you get a Berry flux. This integral of B on the sphere was just 2 pi. Okay, so it's related to that Berry's phase problem, where there's actually something you can calculate to calculate the degree of the map, okay, which is really this the total Berry's phase, the total Berry flux through the entire sphere. Okay, so that's one check. This gives you an integer, and this is some familiar integer that we have seen before. Okay, another check you could do is using this kind of a Dirac theory. Write down a Dirac theory for something in 2 dimensions and ask how many mass terms you could add. Okay, and of course, we are in this particular limit where there is no symmetry, so you're free to add any mass term you like. Okay, so you're imagining that you're poised at some transition between 2 putatively different phases. There are 2 momenta, px and py. Okay, and it turns out, of course, you can write down a third Pauli matrix, tau z. Nothing to stop you, no symmetries. This is class A. Okay, and as you can see, there's no second mass term you can write down. Right. Just a single mass term, so it can tune you between 2 different phases. Okay, and these are 2 different topological invariants. They differ by a topological invariant of 1. Okay, this theory cannot tell you what the total topological invariant is. It just tells you what the difference is as you pass through this transition. Okay, so if this is some invariant C, this is going to be C plus 1 or the other way around. Okay, so that also tells you that there are distinct phases. To actually show that the distinct phases are labeled by integers, you need to do slightly more. You need to sort of double this theory. You need to see that if I put 2 of these topological phases together, let's say I have a phase with mass m and another one with mass m, if I put them together, do they kind of cancel and disappear? That's what would happen for a Z2 classification. Or do they actually add and give you more phases? Okay, so that's a check you can do in the Dirac theory. You can sort of tensor this 2 copies, tensor this with a 2 by 2 matrix, and check if you can add a truly distinct mass term. And you can see over here, the only thing that anti-commutes with these 2 is tau z. If you added m prime, it would still have tau z. You could have another matrix over here. Let's call that mu z. That's this matrix that I've tensored with to give you a 4 by 4 thing. You can add this additional mass term, but it actually commutes with this one. It doesn't anti-commute. And when you do that, all this does is you can add phases together, and you can end up getting it'll split the transitions so that you get 2 transitions where eventually the invariant changes by 2, the 2 copies, but the change occurs in steps of 1, which depend on the sum and difference of these 2 masses. Okay, so there's a little more work in this Dirac theory to going from saying there are 2 distinct phases to actually understanding how the phases combine. Okay, do they combine together to give you additional topological phases, or do they just cancel out? Okay, so this is an exercise to do within the Dirac theory to sort of check this classification. Yes?
So this double theory is like a single 4-component Dirac?
Yeah, you can think of it that way. There are 2 flavors of the Dirac, and they each undergo this parity, the mass changing sign transition. In fact, this is going to be very closely related to graphene. We'll see. But unless there's some additional flavor symmetry, there's no reason for that to happen at the same point. The 2 mass changing transitions could happen at different points. And at each change, the Chern number changes by 1. When the mass goes from, let's say the mass for one of the components is m plus m prime, and the other one is m minus m prime. So these transitions will occur at different values of m and m prime. And you will go through a sequence like that. We'll see in other cases, for example, for the Z2 topological insulator, you combine them like this. You take 2 copies, combine them like that. It turns out you can add a completely different mass term, which anti-commutes with everything, which means you can go smoothly on 2 copies. You can actually go smoothly to the trivial phase. Okay, so that's the second check, and there's a third check I'll do, which is really the purpose of showing you that table. which is to actually go from the result we already know in one dimension up to the result in two dimensions. We're going to Okay, we're going to figure out, given a particular topological phase in dimension D, how to lift it to one higher dimension. Okay, and this comes at a cost, and the cost is that you're going to change the symmetry class that you're in. Okay, so if you start out in class A3, you're going to be able to go up to a different dimension, one dimension above, but it's going to be in class A. And the same applies for class A. If you start in class A, it turns out you can raise by a dimension, but you're going to come back to this class A3. Okay, so there's a way to connect this along these diagonals. Okay, and this will be a mini version of a more expanded connection we'll see next, which is with all these cases which have some sort of particle hole symmetry. Okay, and there this kind of shift will be in dimension and along these eight symmetry classes. So it will be periodic with period 8. Okay, but let's do the case with just two of them right now, this class A and class A3. Okay, so how do you raise the dimension by 1? So let's say I give you a topological phase. So I give you a Hamiltonian. This is this chiral Hamiltonian. So let me call it C. And this is, let's say, in dimension 1. It's a function of K. Okay, and I've made sure that this HC squared is the identity, just flattened it. From this, I wanted to define a Hamiltonian in dimension D equal to 2, which has no chiral symmetry. It's a function of K and let's call it Kx and Ky. And which has, whose topology is preserved by this map. Okay, so two things that are topologically distinct over there map to two things that are topologically distinct in this higher dimension. Okay, and the procedure that you use, it's called suspension. Okay, it's quite simple. You think of a combination of the original Hamiltonian. Okay, and I'm going to multiply this by a coordinate I'll describe in a second, plus the chiral operator, which was tau z. Okay, so this tau z. Okay, so what is this cos theta and sin theta? These are actually going to be the new dimension, ky. Okay, but remember we're on a torus, we're on the sphere. Keep track of this line over here. Okay, so we have the sphere. So this section over here was the original torus, the equator, let's say. Actually, maybe I shouldn't be. So the North Pole is that way. Right, so that equator was the one-dimensional coordinate kx. That's that's this coordinate over here. And then let's say we have another angle, theta. So that's an unusual way to label the theta, but this is really like, latitude, right? Equator is 0, and then you go up to the north and south poles. So this is essentially the other coordinate. Okay, so sine theta is sort of like the new ky. See if I have a different notation here. Or you can just think of theta as being ky, and this kx is this direction. Okay, so the claim is that this construction gives you a Hamiltonian, a gapped Hamiltonian, in 2 dimensions, 2 plus 1 dimensions, which has the same topology as it inherits the topology from this HC in the lower dimension with chiral symmetry. Okay, so you can see a couple of things. One is that if I square this Hamiltonian, it's the identity. Okay, so that comes from the fact that if I square this one, of course, it's the identity, and this anti-commutes with this tau z. It's chirally symmetric, right? So there are no cross terms. There's this square plus this square, cosine and sine are taken care of, and it tells you it's a flattened Hamiltonian, just like this one was before. Okay, the other thing you notice is that it has no symmetry anymore. Okay, now that you've introduced this tau z into the Hamiltonian, it no longer anti-commutes with tau z. Right, this part anti-commutes, but not this part. Yeah, and it's a smooth map. So every time, if I have a pair of Hamiltonians over here that are smoothly connected, the corresponding pair over here will also be smoothly connected. Okay, so this is a way of crossing dimension, and in the process, you lost a symmetry. Okay, now it turns out you can do the converse as well, which is, or whatever, go the other way, which is to start with a Hamiltonian like this, which has no symmetry, increase its dimension, and incorporate a chiral symmetry. Okay, so this is not really a check. This is a way to go beyond what we just said. Just a little bit of an aside that will help us. So let's say I start with H, which is in class A. Let's say I'm going to go from 2 dimensions to 3 now. Okay, then I can define a class A3. Let's see. Now I'm going to tensor it with tau x. So I'm going to increase the dimension of my Hamiltonian matrices. I'm going to double it, multiply by this tau x, and plus sine theta tau 1. Okay, times the rest of it is identity where there was a Hamiltonian times tau 1. Okay, this new thing has chiral symmetry. Okay, because it anticommutes with this matrix 1 times tau z. Okay, so I've created something with chiral symmetry class A3, but you've also climbed a dimension the same way we talked over here. This cosine and sine are like the extra dimensions on the sphere. And you would expect that when you go from 2 to 3 dimensions, the same z will show up as a z for chiral symmetry in 3 dimensions. Okay, so in fact, top insulators with chiral symmetry in 3 dimensions are classified by an integer. And that's consistent with this, with these 2 ways to cross dimension.
Now you doubled the number of bands.
Yes.
And so it seems like you should be able to. This statement over here doesn't refer to any particular number of bands. Whereas, so can one say something about that, or you do it without doubling the number of bands?
So if you want to change the symmetry. If I were to give you some Hamiltonian with n and m number of bands in class A, there's no way you can beat that into class A3, right? So class A3 always has the same number of positive and negative energy bands. So there's a transformation that will take you from a negative energy state to a positive energy state, which is essentially multiplying by this matrix tau z. But all of this classification, the assumption is that you have many bands, and you're allowed to add and subtract bands. And you're thinking of the limit of large number of bands. And in that limit, strictly speaking, all this classification should be done with the limit of n going to infinity, large, many bands above, many bands below.
Well, but it's valid for any number of bands.
It's
But I guess A3 always has to have an even number of bands.
A3 always has to have an even number of
Whereas
bands.
A
Yeah,
is allowed to
yeah,
have an odd number of bands.
yeah, yeah. I mean, sometimes when you
So that's
restrict,
some sense a reason why the factor of 2 is because you got to end up with an even number.
yeah, right, yeah,
Okay.
yeah.
But it's not about a number of bands, right? Like if you have few enough bands, then these classes aren't
Yes.
as you've labeled them.
Yes, that's right. For example, if I had n equal to, if n is 1 and m is 0, for example, right? It doesn't work, and yeah, there are more serious restrictions. If you're very naive and try to classify this just a single band, no symmetry in 3 dimensions, we're going to see by the same logic this 0 goes here and 0. The result for general number of bands is 0. If you have just 2 bands, one above and one below, you can actually get a Z classification again. Okay, but that's very particular to having 2 bands, and in some sense, it's not additive. If you take 2 of these systems and combine them, the topological indices don't add. Okay, so it only really adds when you have large number of bands and you identify those situations which are robust to having many bands. Okay, how much time do I have? 20 minutes, is it?
45.
So I started at 3, right?
Yeah.
So I have till
4:15.
4:15, okay. Okay, so the thing that's really amazing about this integer invariant in 2 dimensions, as you all know, it's the Chern number, is that it's actually related to a physically measurable quantity, right? So let me just say a few words about that. I won't, again, go through the full detail, but okay, so there's a way to write down the invariant for a general band structure, and it's related to the following physical quantity. You can measure the Hall conductance. Okay, so the Hall conductance, as you know, you apply. This is a electrical insulator, but you can still apply a voltage this way, and you measure the current in the perpendicular direction. Okay, and you look at the current for a particular voltage that you apply in this cross direction. That's the Hall conductance. Again, you can write down an expression for this Hall conductance. You can write it in terms of the current operators, Jx and Jy. It's just the derivative of the Hamiltonian with respect to the momentum. Okay, that's what gives you the current operators. And the Kubo formula tells you that this someone in. Okay, so you can derive a Kubo formula just from usual response theory, apply a voltage, see how your wave functions change, calculate the current in the new wave functions, and it turns out that you get this relation to some sort of correlation function of the currents. Okay, and you can show that this is actually related to this invariant. This integer invariant that we defined. Okay, this 1/2 pi is we're working in units where e squared and h bar are set equal to 1. Okay, so if you multiply by e squared over h bar, this will give you e squared over h times this Chern number. Okay, so that's one of the rare cases where this invariant, of course it has connection to edge states and so on, but here it has a very direct connection to a physical quantity that you can measure. In fact, that's how people, it's quite easy to actually detect whether you're in one of these integer quantum Hall states. Many examples of that now. And we'll see some examples in graphene as well soon, maybe in my talk tomorrow. Okay, so another connection you can make. So when we change these number of parameters, we were thinking of dimension. This invariant goes to an invariant in a different dimension. But the additional parameter that you add could actually be a parameter. Okay, you could still be talking about a one-dimensional system, but with some additional parameter that breaks chiral symmetry. Okay, and in that way, you can relate this integer over here to a Thouless pump. So there's a way in which you can think about this generalized Hamiltonian for the one-dimensional system. And this M prime is really some external driving parameter. You go through a sequence and you come back to the original state, and you find that you've pumped one charge. Okay, that's in my notes as well, but I don't have time to discuss that. But it's important to understand that this classification is more general than just talking about insulators in various dimensions. It could be insulator in a particular dimension, extra parameters are something else. Okay, and they give you different consequences. Okay, so finally, let me talk about the rest of the entries in this table, which require you to add more symmetry. Okay, and so the first thing we have to do is to understand what symmetries should be considered at first, and then we can try to construct this table. Okay, so we'll be interested in situations where the symmetries are internal, so they don't involve any change of the spatial coordinates, so no spatial symmetries. One reason to think about that first is to think about states that are actually robust to adding disorder. Okay, another reason is that when you have a surface, we're often going to be interested in surface states. We want to make sure you don't break the symmetry at the surface. Okay, and when you talk about spatial symmetries, reflection or rotation or something like that, the surface could break the symmetry. In which case, although you may have something topological, you may not see it at the surface. Okay, so to really make this tight association between a topological bulk and something gapless at the surface, you want to consider internal symmetries. Okay, things that do not change the spatial coordinates. Okay, so let's focus on internal symmetries. These are robust in the presence of disorder, or can be. Yeah, and at least in free theories, it's always symmetric at the surface, and so on. Okay. So now the question is, what internal symmetry should we think about? For example, should we think about spin rotation symmetry, or some maybe situations with spin rotation, or time reversal. So one can think about various symmetries, but it turns out that symmetries that are implemented as unitary operators, like spin rotation symmetry, they can be handled very easily. Okay, so you can just find representations of this spin rotation symmetry, different spin, and within each representation, you can simply solve this problem. Okay, so these are easy to handle. Unitary symmetries are easy to handle. You just label by quantum numbers, basically. You label your fermion operators by quantum numbers, and that kind of takes care of that. So the thing that is harder or more interesting to take care of are the anti-unitary symmetries. Okay, so for anti-unitary symmetries like time reversal, there are no quantum numbers. Okay, you have degeneracies, you have various effects of the symmetry, but it's not due to the simple notion of quantum numbers, of representations of that symmetry. Okay, so those are the ones we really want to focus on. We want to focus on anti-unitary symmetries. Okay, so we're thinking about single particle theories. So, for example, let me call theta the time reversal operator. Okay, and it will usually involve complex conjugation. We call it K. Okay, so you'll take the wave function, you'll do complex conjugation, and maybe you'll do something else, which is part of the time reversal. Okay, so there's another thing you want to think about, which is charge conjugation symmetry. Okay, so actually, let me complete this. You want to think about Hamiltonians. Okay, so under this time reversal symmetry, that's the momentum changes sign. Okay, but apart from that, nothing should happen. That's what tells you that this is a symmetry of the Hamiltonian. Okay, so we want to think about Hamiltonians like that. We also want to think about charge conjugation. You can call it a symmetry, but the way it acts is actually slightly different from a symmetry, at least on the one particle Hamiltonian. So this is also anti-unitary. Okay, and it involves some complex conjugation. But instead of bringing the Hamiltonian back to itself, it actually changes the sign of the Hamiltonian. Okay, so you can ask, is this a symmetry at all? If this was one particle physics, you wouldn't call this a symmetry. You're taking something at energy E and you're relating it to an energy level at minus E. Okay, but remember, we are actually thinking about fermions. At the back of our mind, we are actually thinking about a many-body problem where we're going to fill all the negative energy states. Okay, so if you have a relation between a positive and negative energy eigenvalue, this can actually lead to degeneracy. Okay, you can either have an electron in a particular energy level, or you can empty a negative energy level and get a hole, and those two will have the same energy. Okay, so this charge conjugation can actually lead to degeneracy. It can actually be a symmetry of the system. Okay, it's not always. Sometimes you can't really think of these two levels as being independent, but this is something that you need to consider when you think about classifying the one particle physics of these given by these block Hamiltonians. Okay, and it's relevant, of course, for superconductors. Okay, so in superconductors, you have particles and holes that are mixed by the superconducting order parameter, and you always get some operation like this that relates the particles and holes. Okay, so you have these two anti-unitary symmetries, and you have three options for each. Like we said before, you have an anti-unitary symmetry. It can either square to plus or minus 1. Similarly for this particle-hole symmetry. Okay, and of course, not having the symmetry is also an option. So in some sense, 0 is also an option. Okay, that means not having symmetry. Okay, so it looks like there are 9 possibilities, right? So you'd think that there are 9 classes. Okay, either have time reversal, square to plus 1, square to minus 1, not have it, similarly for charge conjugation. Okay, but it turns out there's an additional one because you could have each of them being 0. Okay, in the sense that you do not have time reversal, you do not have charge conjugation, but you may have their product. Okay, you may have the product of time reversal and charge conjugation. Okay, so let's call it pi is theta times psi. Okay, this thing is a unitary symmetry. This is actually our chiral symmetry. Okay, this is unitary because it's a product of two operations that both involve complex conjugation, right? So this is a unitary symmetry. This is a unitary operator, and it could be that you're both 0 over here and not have chiral symmetry, or it could be both 0 over here and you could have chiral symmetry. Okay, so there are two options there. So you've got to add one class. Okay, so this additional class is actually this class A3 that we talked about. Okay, that's the class over here where you don't have either of them, but somehow you have the product. The combination is present. Okay, whereas the class A is you have neither of them. That's the 0, 0 entry. Okay, and then you can list out all the other options over here. For example, you can think of a case where you do not have particle-hole symmetry, but you have time reversal, and it squares to plus or minus 1. Okay, so let's look at that over here. Time reversal squares to plus 1. or squares to -1 without particle hole. Okay, so squares to +1, this is actually slightly strange for time reversal acting on electrons. But if you have electrons where there is no spin-orbit coupling, you can really think of the spin as being independent of the spatial degrees of freedom. You can simply use charge conjugation to represent time reversal. Okay, you don't have to flip the spin. Okay, so that corresponds to this class A1. Time reversal is just charge conjugation. Okay, and but the most standard time reversal symmetry for electrons involves a spin flip. Okay, you do complex conjugation, and then up and down get exchanged with the minus sign for one of them, and that's this case where theta squared to -1, but there's no particle hole. You know, it's an insulator. It's not a superconductor. There's just no charge conjugation symmetry. Okay, so this is the class which has these topological insulators, and this is the one where the weak spin orbit coupling relevant to things like graphene is this class A1. Okay, the others are various kinds of superconductors. Okay, so class D is just a superconductor with no symmetry. Okay, it has no time reversal symmetry. It has some particle hole, but this is just expected for any superconductor. Okay, the natural, the square of the particle hole conjugation +1, that's the natural sign. That's what you get in systems with spin-orbit coupling. Just like theta squared to -1 is the natural sign for spin-full electrons, and this class D3, superconductors that have time reversal symmetry, this is realized by helium-3. Phases of helium-3 realize the topological phases in this class in 2 and 3 dimensions. Okay, so it turns out I'm kind of running short on time, but you can probably believe that there are ways in which you can walk through these classes as well. And in fact, there's a way of drawing these classes which kind of makes this clock more apparent. So we're going to draw two axes. Okay, so this is theta squared and this is psi squared. And there are two values, ±1, there's 0 as well. 0, 0 corresponds to the class A and class A3. Okay, they form a pair by themselves, but the others are arranged on the square. Okay, so theta squared +1, no charge conjugation. This is the class A1. Complex conjugation is time reversal, and this is class A2, regular time reversal insulators. Okay, and then over here you have theta squared is +1, and this particle hole squares to +1. This is called BD1. Okay, and then here we have no time reversal, but particle hole squares to +1, the natural sign with spin orbit. And then you have D3, this helium-3 kind of analog. A2, and then here you have the unusual sign of particle hole square. Okay, so these are superconductors that have some sort of spin rotation symmetry. You combine particle hole and spin rotation to get some weird minus sign for the charge conjugation. This is called C2. Okay, and this is C and this is C1. Okay, so this class C is also interesting. It's what people call a D plus ID superconductor in 2D. Okay, so you have spin singlet superconductor, D wave, but with some time reversal breaking, you can have chiral edge states, rather like this class A, but in a superconductor. Okay, so just to familiarize, this is helium-3. Okay, so it turns out that there is a relation between these, which can be proved in a way very similar to what I mentioned before. So let's label these with some integer s, which runs from 0 to 7. Okay, different classes. So what you can show is that the classification, let's call it K. So this is related to K theory, so it's called K. But this is just some group. It's like Z or Z2. I'll call R because these are supposed to be the real classes. This charge conjugation gives you some sort of reality constraint. In contrast, these two are called the complex classes. They'll be called KC. Okay, so the S over here runs from 0 to 7, and you're in some dimension D. you can show that this is equivalent to moving one dimension up this clock and also rotating the clock clockwise. Okay? And this is very similar to what we did for the complex classes. So in complex classes, the S is just 0 and 1. Okay, we said that they're related by raising S by 1 and D by 1. Okay, of course, when you have just two of them, it doesn't matter whether you raise or lower. All of this is interpreted modulo 8. Okay, this is mod 8 and this is mod 2. Okay, and the procedure is very similar. So for example, let's say you start in a particular dimension in class A1. You have a Hamiltonian in class A1. It has a time reversal symmetry. You want to raise the dimension, and you can do that. And at the same time, you can invoke a chiral symmetry. Okay, you can add to the Hamiltonian a chiral symmetry, expand the matrices, multiply by tau x and tau y. You get something with chiral symmetry now. And that the combination of that chiral symmetry with your original time reversal gives you a charge conjugation symmetry. Okay, so you have both theta squared 1 and psi squared 1. Okay, and then you can go one dimension higher, just like we did before. You can lose the chiral symmetry. You take some Hamiltonian that has chiral symmetry, add actually the operator that anticommutes, and in that process you end up losing that chiral symmetry. So you lose one of the two. You lose either time reversal or particle hole. In this case, you keep particle hole and you lose the time reversal. The only thing that you need to work out over here is how these things square to plus minus 1, how that changes as you go around the clock. Okay, and that's in my notes. That's just doing this in a little bit of detail, creating this chiral symmetry operator, and just checking the algebra. Okay, but at the end of that, by a process very similar to this complex class that we discussed, you end up with this relation. Okay, so when you move in dimension, you also move in along the clock. Okay, so this actually tells you need to know very little to fill out this table. For example, if you just knew the classification of topological phases in one particular dimension, for example, in dimension 1, you could completely fill out this table. Or if you knew just for one symmetry class in all dimensions, if you knew the classification, you could fill it out. It also tells you don't need anything more than 7 dimensions. This thing repeats after that. You go to 8 dimensions, it's the same as 0 dimensions. Of course, you may not want to go to 8 dimensions, but if you did, right, it would come back. And we'll see one example where some of the 6 and 7 dimensional entries are actually going to be important, although we're not doing string theory, right? We're going to do graphene. So it's actually this, you have to understand it in totality, and it actually helps to think about it more generally in different dimensions. Okay, so let's just fill out a few examples that we know and use that to fill out this table, okay, in the remaining 10 minutes. Okay, so in class A1, actually using this kind of analysis, you can actually show that there's nothing in 0 dimensions. Okay, and there's nothing in 1 dimension. There's no Chern number, for example, because you have time reversal symmetry. Okay, and do I want to invoke 3 dimensions? There's nothing in 3 dimensions as well. You would have heard about it if there was, right? Right. So anyway, so let's put those in. Okay, what else do we know? We know class A2, famous topological insulator Z2. Again, you can use this Dirac theory, very simple way to classify, and show that this is a Z2. You take 2 of them, add them, you can make them trivial. 3 dimensions, there's also Z2, famous 3D topological insulator. There's nothing in 1 dimension. Okay, what else do we need to know? Okay, so let me also tell you that in class C, in 2 dimensions, there's something called 2 times Z. That's this D plus ID superconductor we talked about. It has 2 edge states because it has both spin up and spin down. So it's always, in some units that are natural, it's always 2 times an integer. Okay, compared to some other, this integer over here, it's sort of 2 times what you would get if you had a quantum Hall state. Okay, and I think I need one more. Let's see. So I need a Z somewhere. what would be a good Z to motivate over here?
D3. Class D3, I think, in 3-dimensional class.
Yeah, so class D, think about superconductors, no symmetry, they have chiral edge states.
Yeah.
So this has Z. Okay, so it's very much like the Chern number over here, except these can be Majorana fermions, this is the topological superconductor everyone's looking for. Okay, so let's do this, and from this, let's fill out this table. Right, so okay, so we have these zeros, so they're going to propagate. Okay, so that collides and that comes out here, right? Okay. Similarly, this 2Z. Okay, and what about the Z2s? So okay, so that sort of completes this table, and you can kind of see some interesting things that appear. One is, for example, this classification in 0 dimensions. Okay, so it's maybe interesting to try to understand this. So every time you have a conserved charge, there's a Z, except for A2, which is 2Z. Okay, so this is really the number of Kramers pairs that you have below below the chemical potential. These are the number of levels you have below the chemical potential. At least that's how I interpret this. There's some question how that fits in with this sort of stable equivalence, but I think that's sort of the idea. And here they are fermion parity. If you like, these Z's are really the trace of the Hamiltonian, and these Z2s are like the Pfaffian of the Hamiltonian. Okay, these are antisymmetric matrices. They're Pfaffian. That's sort of just quantum mechanics, right? 0 dimensions. So then in 1 dimension, what you discover is that in class D, there is a Z2. Okay, so this is really the Majorana chain that people are trying to make, trying to get these 1-dimensional superconductors that have Majorana 0 modes at the ends. And within this table, they are in some bizarre way related to 3-dimensional topological insulators. Right. Okay, and what else? So you also have, this in 2 dimensions. You have, for example, class D3. There's a Z2. So this corresponds to PX plus IPY superconductor moving right, and a PX minus IPY superconductor moving to the left. So you can make the combination doesn't gap out. And then there are these two. This is the promised thing I mentioned. These are in 6 and 7 dimensions. That's when you get topological phases for this class A1. Okay, I should also mention there are all these entries in 4 dimensions, which are the 4-dimensional quantum Hall effect. Okay, at least some of them are. Okay, but what is the Z2? Is the Z2 ever relevant? So it turns out that if instead of regular time reversal, you have the product of time reversal and reflection. Okay, we talked about this as being a symmetry that leaves K invariant. Okay, unlike regular time reversal. So what about classification under this symmetry? So we are stepping out of our usual comfort zone because we're using a spatial symmetry reflection. But let's just do that for a second. It turns out the same classification works with this thought of as time reversal symmetry, except all of the dimensions should be reversed. Okay, so the dimension, if you want the classification in dimension D, you should actually look at minus D. Okay, and minus D means 8 minus D. Okay, so any spatial, this peak transforms like a spatial coordinate under time reversal. You have to reverse the dimensions. So these are actually relevant to this PT symmetric Hamiltonians in 6 and 7 dimensions, in 1 and 2 dimensions. Okay, and this is going to appear in our talk tomorrow about graphene, because those are actually the topological invariants that are going to be important when you think about graphene. Okay, you have time reversal, you have reflection symmetry, you have inversion symmetry, rotation by 180 degrees. The combination will give you some topological index in 1 and 2 dimensions. Okay? In fact, this one-dimensional index protects the Dirac point of graphene, and this is some other interesting index that appears in this twisted, this magic angle bilayer graphene. Okay, so yeah, so maybe I'll stop over here. So,
Let's thank our speakers. Anyone have any questions?
So if you look at the columns of the plot you drew,
Uh-huh.
so on the left column you have C, and in the middle column you have A, and there's some structure to the naming. And then if you look at the right column, it's kind of all throughout the window. You have D, and then D3, and then BD1. Is there any reason behind that besides just like artifacts from?
Yeah. Yeah, so this is all due to one person called Cartan. You should complain. I mean, he's dead actually, so you can't complain. But yeah, so he named. So this it's also related to some geometrical spaces. So all these are some spaces that are like spheres. They have uniform curvature, and he had some way of naming them. They seem almost reasonable. Like yeah, you're right. You would have wanted him to call this D1.
Yeah.
Why BD1? I don't know. Yeah. Maybe someone knows. Maybe there's a good reason. Or maybe it just, it's lost, it died with him. So, yeah, and this one should be, I would have said this should have been, this D3 should have been D2, right? Yeah, I don't know what it's D3. Yeah.
So it seems like in this construction, you're showing that the classification has to be at least as big as preceding classification. But how can you show that's not actually bigger than, or like, say it's like, some extra subgroup that you haven't found yet, for instance? How do you know that it's exactly as big as the preceding one when you're going to diagonal columns?
Yeah, so you've got to argue two ways. So one thing you can show very easily is that if I have two phases that are related in the lower dimension, same equivalence class, they are related in the higher dimension. Because there's a smooth path for one, there's a smooth mapping over here, and that's done. The thing that's harder to argue, but which is true, which I leave as an exercise, is two things that are apparently distinct in the lower dimension. With this construction, they should be distinct also in the high dimension. That is something that you have to think about. But that's what this suspension procedure, you derive a contradiction basically, that happens.
So is there physical cases of A3 where those chiral symmetry is robust against disorder or those kind of things? Like usually it's some subdata symmetry or some certain symmetry that breaks in system into two part and only
Yes. Yeah. So one place that has appeared is in the half-fill Landau level. Again, it's not a perfect symmetry, but half-fill Landau level has sort of a charge conjugation symmetry, and that's a combination of charge conjugation and time reversal.
Yeah.
And it's approximately symmetric. So again, it's not exact, but the approximate symmetry is important for the so-called Dirac composite fermions. But that's where A3 has appeared.
But do they break a particle hole or like?
So having the higher Landau levels effectively breaks the particle hole.
Oh, but only with
Yeah, and
combination of
disorder also breaks the particle hole. But
Right.
you can think of when people do numerics,
Uh-huh.
lowest Landau level projection, they literally have particle hole.
I see.
It's class A3 in some sense. And there's some interesting duality between that and class A2. But there's some very special duality. It holds even for interacting systems between the Z2 and some part of the Z, which is really like a strong weak coupling duality.
Okay, well, let's thank our speaker again.